So the next talk will be given by Jed, and he will talk about synchronization synthesis for network programs.
All right. Hi, everyone. I'm Jed, and I'm going to talk about synchronization synthesis for network programs. So this is joint work with Hossein at RIT and my advisor, Pavel, at University of Colorado Boulder. Okay, so the first point here is that networks are complicated. This picture is kind of an extreme example. Hopefully, actual networks do not look like this in your application, but the point here is that there are, even in realistic networks, hundreds or thousands of interconnected devices. So behind this mass of wires here, you have many switches through which packets flow between different end hosts. And somehow we need to reason about global forwarding behavior between these end hosts, which is often referred to as a configuration. Software-defined networking, or SDN, helps a bit by giving you the abstraction of centralized control. So in this picture, this network operator is able to control many different devices through this one terminal here. It also gives you a standard API, which lets you add forwarding rules to affect the way traffic flows through devices and other types of commands. The other thing that SDN is good for is allowing high-level languages to be built on this. So rather than contacting individual devices to install pieces of the configuration, you can specify in a high-level language what your configuration looks like and build that on top of SDN. So unfortunately, there's still problems even in this context of SDN. So I have a couple articles here from 2016. Twitter went down because of internal code change. Google apologizes for a cloud outage. So beyond just annoying users in these various platforms, these types of problems can cause huge impact for these companies. So at the bottom here is a report from 2016 that found that the average cost per minute of unplanned outage was almost $9,000 US, and the average cost per entire outage was almost $750,000. So worse yet, the number of human errors accounts for about 22% of all outages in this report, at least. Okay, so the point here is that networks are programmable systems, and human error can have severe consequences. Okay, so how can we address that? In this talk, what we do is consider various races arising in network programs, and we focus on preventing those. So in particular, we classify races as either packet races or controller races. So packet races are when ordering of packets or control messages results in unexpected global configurations, and control races are when two different otherwise correct network programs or modules interleave to cause unexpected configurations. Okay, so we're going to present an approach for first how to write, correct, and efficiently implementable sequential network programs, and then how to fix concurrency bugs when several of those programs operate at the same time. And to get a little more specific there, first we're going to introduce a carefully designed programming model for network programs, and that's going to enable us to do an efficient counterexample guided approach for synthesizing synchronization in those programs. Okay, so the first part is how to eliminate packet races. So let's look at an example where a packet can trigger a configuration change. So this picture is what's known as the stateful firewall, and incoming traffic along the green path is only allowed after basically outgoing traffic has happened. So let's try sending a packet from H1 to H4. And when the packet arrives at switch S4, the switch knows that this is an event, and it knows that it needs to somehow set up the incoming path. But in the meantime, right, so the switch sends a message to the controller to notify it about this event. It also forwards it to the destination. In the meantime, though, the destination replies, and only then does the controller respond to set up the incoming path. So this is a problem, and we refer to this as a packet race. and we need guarantees about when the configuration should change with respect to those events. So in particular, don't respond too late or too early to events. And this is solved by a model we call event-driven consistent update in PLDI 16. And part of the idea of that paper is a programming model based on Petri Nets. So the basic idea is event-driven transitions between configurations, where configurations correspond to these circles or places in the Petri net, and events correspond to the squares or transitions. And so in this talk, I'm going to refer to a one-safe Petri net labeled with configurations, like shown in the picture here, as a Petri net program. Basically, the state is defined by where the tokens are, and the current configuration is the union of the configurations on those places that are marked by tokens. Events can also fire by consuming tokens from an input place and placing them on an output place. Okay, so these programs can encode important constraints between events. So on the left here, we have sequencing. Event A happens before B. And then we have conflict. Only C or only D can happen, but not both of them. And then we have concurrency. E and F can happen independently, basically. So in this paper, events are simply things that cause the system to move between configurations. So we're agnostic to actually what network packets or phenomena cause the events. And another piece of our model is what we call locality. Each event needs to have a location, and conflicting events like C and D in the picture here need to occur at the same location. And what that gives us is freedom from this first type of races, or packet races. And it also gives us this result from the PLDI 16 paper that given a Petri net program that doesn't satisfy locality, you can't correctly implement it without sacrificing availability. So in a sense, what this is saying is that Petri net programs are the right model for network programming. So to be a little more specific, if a program doesn't satisfy locality, either you need to do buffering, which is expensive in running network, or you need to change a state change state in a way that's not eventually consistent. Okay, so we talked about how to eliminate this first type of races. Now let's talk about the second type of races. Let's look at an example here where you have a network, and this network is being managed by now two controllers. The top of the network by controller 1, and the bottom by controller 2. And let's say that the configuration or the global forwarding rules look like this. Initially, traffic is being forwarded from H1 to H2 along the solid paths, and the operator wants to take down the initial path and set up this configuration which forwards from H3 to H4. But the operator also wants this isolation property, which says that all packets entering at H1 need to exit at H2. Okay, so hopefully you can see that there's a potential bug here and that it's different from the previously described packet races. Basically, if this controller 2 starts changing over to the violet rules first, it can cause a violation of the specification. So if traffic is now forwarded H1 to H4, violating isolation. So in this approach, we want to synthesize synchronization constructs in order to prevent those types of bugs. Okay, so how can we model synchronization in these Petri net programs? One-safe Petri nets have a good way of doing this. So we have in this paper 3 types of synchronization skeletons, we call them. And on the left here is a barrier. Basically, events A and C need to happen, both of them, before B or D can happen. And then in the middle condition variable, A has to happen before C. Mutex A through B inclusive cannot interleave with C through D inclusive. And the goal of our synthesis approach is to generate these types of skeletons to avoid violations of those properties. Okay, so let's look at an example of how our synthesizer works. This is the Petri net program corresponding to the previous example with the 2 controllers. The left Petri net with red and orange corresponds to controller 1 and the other controller 2. Firing event A corresponds to taking down the red rules, and firing event B corresponds to bringing up the orange rules, and similarly with the other Petri net. Okay, so we can specify the isolation properties. In this paper, we specify them using LTL. So no packet originating at H1 should arrive at H4, and similarly with the other one. And if you check this first initial Petri net, you get a counterexample. Namely, if C fires and then D fires, the token on the right moves down to violet, and that violates the specification as we saw previously. So our tool takes that counterexample and it generates a skeleton that eliminates that one. So here's that one. But this second Petri net also has a different problem. So if we fire A and then B, the token on the red node can move down to orange, and that violates the specification in a similar way. And so we give both of those to the synthesizer, both of those counterexample traces, and it gives us a synchronization skeleton that avoids both of them. And you can see here, this is a barrier that requires both the red and the green token to move before the other ones can be brought up. Okay, so here's the architecture of our synthesizer. The user will give a buggy program in terms of a set of Petri nets that have bad interleavings, and the user will also give a correctness property that specifies what are the correct interleavings, and the synthesizer will return a program with added synchronization. Okay, the verifier on the right, it returns a sequence of events that leads to a particular violation of this property in some network configuration. And it also checks one safety of the Petri net. And then the synthesizer produces a Petri net program that satisfies all of those counterexamples seen so far. Okay, so this is kind of details about how the synthesis part of this works. So we have, this happens in Z3 SMT solver. So we have these variables, Petri, mark, and location, that represent the current synthesized Petri net. The region highlighted in green is static, and that corresponds to the input Petri net. And these white regions corresponding to added places and transitions, those will be filled in by the synthesizer as it adds synchronization skeletons. Okay, so each of these cells corresponds to, the cell on the left corresponds to edges between place M and transition N, as you can see here on the right in the picture. And the mark is a Boolean variable which says whether that place is marked in the resulting Petri net. And the way that we encode, the way that we make sure that the Petri net has synchronization skeletons added instead of just arbitrary transitions and places, is each of the rows in this set of variables corresponds to a single synchronization skeleton. So the first item is what type it is, either mutex or condition variable, etc. And then these middle ones correspond to which of the processes of the input you are adding the synchronization between. And then the last one just reserves different places and transitions in the grid from the previous slide. Okay, and then we also have constraints based on the finite set of counterexamples seen so far, so that those are avoided by any Petri net that's synthesized. Okay, so we ran several experiments, and I'll talk about one of them here, which is a scaled up version of the previously discussed isolation example. So what we did here is, in the lower left, you see this NSF net from the topology zoo topology set. This is a network of nodes, wide area network across the United States. And we can superimpose similar configurations on top of these larger networks corresponding to the isolation example. And then we measured total synthesizer runtime versus the size of the topology. So for the topology zoo set, we had networks up to size 750, and the total runtime was less than 4 seconds. We also generated highly connected random graphs, and we scaled these up to 1,000 nodes, and the total runtime was less than 7 seconds for that one. And then we also generated large fat tree topologies, which are commonly used in real data centers. And this scaled up to over 1,000 switches in less than 100 seconds. Okay, so there's some related work. These languages, Frenetic and Netcat, allow programmers to specify static configurations, but we want to reason about event-driven configuration changes. So these approaches allow event-driven programming, but they don't address correctness, such as when to respond to events or how to deal with packet races. And this is our previous work from PLDI 16, which addresses correctness, but only in the context of a single event-driven program. And it doesn't consider controller races between multiple event-driven programs. This is an approach which formalizes how configurations can change, but doesn't consider events in that context. And there's some custom search-based algorithms for producing network programs from specifications, but none of these use counterexamples to speed up the search. And then there's like a large volume of different synthesis and repair approaches for Petri Nets, but these solve different problems that we can't directly use in our context. Sorry. And that's it. Thanks.
Thank you.